Okay, the bulk of today's talk will focus on homogeneous hydrogenation reactions, now integrating all the general concepts that we've learned up until this point. But I do want to finish by concluding briefly the discussion that we had at the end of last time about the underlying principles of catalysis. And actually this complements each other nicely, because we'll talk about the theoretical principles, and then we'll see directly how they apply in catalytic systems. So at the end of last class, we discussed different experimental techniques you can use to determine distinguish between homogeneous and heterogeneous catalysis. And so I'll just leave those notes up very briefly in case anybody didn't get a chance to jot them down from last time. And then just in terms of defining terminology and different nomenclature that you'll see throughout the class as we transition to asymmetric catalysis, you'll hear terms like prochiral, and this just refers to any position on an achiral. That was probably confusing. On an achiral molecule that becomes chiral center upon addition of a new group to either one face or to or replacement if it's not a sp2 hybridized atom, but replacement of a substituent. And so prochiral molecules have stereochemical associated terms with them. One that you'll encounter is Reface versus Cyphase. Every now and again, I'll hear people say that a Reface is converted to R and an Cyphase is converted to S, and that's not quite right. That can be right depending on the reaction, but is not inherently right. So the Re versus Cyphase of a molecule comes from just putting it in the plane of the page and then assigning priorities using standard Kahn-Ingold-Prelog convention. And then the face that is associated with a clockwise rotation is the reface, just an analogy to R. And the face that's associated with the counterclockwise orientation is associated with the Cyphase, an analogy to S. And then if your prochiral molecule does not contain an sp2 center, then Re and Cy don't apply. And so the terms you'd use there are pro-R and pro-S. So to illustrate that point, I used this hypothetical CH activation reaction where we'd be able to distinguish between these two prochiral methyl groups to put, for example, iodine substituent. And I've defined here what then is pro-R and pro-S by reading out the stereochemistry of the resulting product and then backtracking. Okay, any questions on that? Now I'll go through this very quickly, and you don't necessarily need to write this down because I think these are probably all things that you've encountered before. Descriptors for stereoselectivity, and part of the reason I have all this written out is just to make one point. So in the early days, the most convenient way to measure, let's say you run some reaction that you hope is stereoselective, like in the early days where they were where the Sharpless lab was developing their asymmetric epoxidation. The way that you would measure the level of asymmetric induction was to take the optical rotation of your final compound of unknown enantiomer enrichment and compare it to typically a standard that was known to be enantio pure. And so what was used, the optical purity, which is just defined as the ratio of the optical rotation of the mixture and the optical rotation of a single enantiomer, is conveniently this metric that we use so commonly these days called EE. So the reason why we use EE as a field, it ultimately stems from the fact that this was the most directly came out of the most commonly used measurement back in the day. Of course, now we don't measure optical rotation unless reviewers ask us to, or journals have that standard, because we can measure an enantiomeric ratio directly using chiral, HPLC, chiral GC, SFC, etc. And so enantiomeric excess is just defined as the ratio between the concentration difference or the quantity difference between the major and minor enantiomer divided by the sum. And there's been a movement within the field that many people advocating that instead what paper should report is ER. And the reason that this is attractive is because then if you take the log of the ER, you have a direct correlation to actually the delta delta G double dagger of the reaction. So the ER, unlike EE, ER has a direct meaning in terms of the underlying energy involved. So when you're doing things like making a Hammett plot, you have to be careful, take care to not directly plot EE versus, your sigma constant. You need to convert to ER and then take natural log and plot that against sigma constant. And then selectivity factor. This is just a descriptor that's used for kinetic resolutions, and it's defined as drawn here. I won't go through the details of that. I think it's the kind of thing if you need to calculate S for a project you're doing, you'll get familiar with it when you need it. And then some rules of thumb that I find personally helpful are just thinking about what are the actual energy differences, what are the actual delta delta G double daggers involved when we're talking about a reaction that's 80% EE or 90% EE, and those are shown here. So a delta delta G double dagger of 1.6 kcals per mole translates to about 80% EE, and then only a 0.6 kcal per mole increase gives you 10% more in EE. And so this area of asymmetric catalysis seems to be obsessed with 90% EE, and I don't know the historical origin of that, but that seems to be what everybody has agreed as a highly selective reaction. And I always find that just a little bit curious because, in terms of the underlying energies, what is the difference between 87% EE and 90% EE? It's really almost nothing, but that argument doesn't seem to be convincing to reviewers. Okay, so now we'll talk about a few different general models by which stereoinduction can take place, and then we'll see how this plays out in the context of hydrogenation systems. One of the terms I want to define is the enantio. So in any catalytic reaction, of course, these have multiple elementary steps. And the enantio determining step is not necessarily the step that intuitively seems like the one where like the stereocenter is formed, for example, where the new bond is formed. The enantioselectivity determining step is the step that is the first irreversible step that takes place through a diastereomeric transition state. So let's say you're doing some hypothetical enantioselective CC bond forming reaction, and the CC bond forming step is reversible, then the enantio determining step would be something potentially downstream of that, like product dissociation. So we want to try to be clear in this class of that terminology, and then you want to be clear when you're writing manuscripts, for example. So let's consider a couple different case studies of what the energy landscape can look like for different types of enantioselective reactions. We'll consider the very simplest case first, which looks like actually just the energy diagram of like any catalytic reaction, essentially. So the simplest situation, these would include things like atom or group transfer reactions. The specific example I've drawn out here is oxidation of sulfides to sulfoxides, and some epoxidations also go through this model, where basically you have you don't need to worry about any product association, pre-association step or anything like that. You have a reactive group that's going to be transferred on your catalyst. In this case, it's a metal oxo. And then the only thing you need to worry about is the collision between that metal oxo and the reactive nucleophilic moiety, whether it's a sulfide or an alkene. And so here the situation is very simple. You have a single enantio, a single turnover limiting and thus enantio determining step, which is just this collision event. And then the delta G double dagger is the difference between the transition state energies between the minor and major pathway, and that will then translate into the empirically observed EE or ER. But many or most catalytic asymmetric reactions are not so simple. And so let's consider now this alternative scenario where you have some reversible step or some step that at least in principle could be reversible prior to an enantio determining step. And these are more complicated. And this is often the case when we're talking about hydrogenation of olefins, which is obviously the main focus of today's class. So let's consider two different scenarios now. So we're looking at this hypothetical reaction coordinate or this energy landscape. We're going to start with the purple dot, which is just the alkene substrate of interest and the catalyst of interest with a generic P bidentate ligand. So think something like BINAP, for example. And these are just apart infinitely far in space. So the first thing that needs to happen is these two will find themselves. There's some barrier associated with that coordination step. And then you will get to two intermediates that are diastereotopic, where the alkene can either coordinate on the open coordination site to one face or the opposite face. And these two diastereomeric intermediates will have different energies associated with them. As drawn, the red one is more stable. And probably what you'll appreciate is from the purple arrow, after we bounce over these first hills, now the lowest energy process to proceed forward is not to go back to dissociate the alkene, it's actually to progress further in the hydrogenation. In this case, it would be coordination of H2, oxidative addition, and then all the elementary steps that we'll talk about: hydride insertion, CH reductive elimination. And so where an enantioselectivity is actually determined is just in the alkene binding event. And so to describe that formally, this means that the interconversion of the diastereomeric metal olefin complexes is slow relative to the rates of conversion of those intermediates to product. And now the opposite sort of situation can take place, where that interconversion is fast, or that interconversion is at least competitive with the rate of conversion to product. So let's consider that now, scenario number 2. So now again, starting, and I won't redraw these, starting at the purple dot, now we have alkene coordinating, but this process is fast and reversible. It's flying on both faces of the alkene. It's sampling both of these states. And thus, enantioselectivity is determined not by which of those is more stable because they're interconverting rapidly. It's determined by the activation barrier of these next steps. So hydrogen coordination, oxidative addition, et cetera. And so within this general scenario, there are multiple possibilities you could consider here. Either the more stable diastereomeric intermediate reacts faster, and that's what's drawn, or the more stable one could react slower. And so then the EE of the reaction is determined or is a function of what I've highlighted here, delta delta G double dig, the barriers between these two steps. And if you think about this, this not only reflects the activation barriers, but also the relative stabilities of the intermediates involved. So that's the key determining factor. And so this general phenomenon of more complicated processes with reversibility happening prior to an enantiodetermining step is called Curtin-Hammett control. Any questions on that?
So both scenarios are Curtin-Hammett?
Yeah, this is a little bit, I think, a little bit complicated. If you as most rigorously defined, I think Curtin-Hammett can refer to a couple different subcategories of reaction. But people, when they're in writing papers, people most commonly use it to refer to a situation like B, where the more stable intermediate is the slower reacting intermediate, because that's, I think, the most sort of clear-cut demonstration of the principle, if that makes sense, Camille. But yeah, I think Curtin-Hammett control in general would just refer to a process involving a pre-equilibrium step that needs to be accounted for in an enantioselective process, if that makes sense. Okay, so now let's talk about some of these ligands that we've already seen, and we're going to continue to see throughout class, and different descriptors that will be useful and rigorously define them. Some of these have come up before, but now we'll just go ahead and rigorously define them. So one class of ligands you've seen again and again already are phosphine ligands. They're among the most important. Part of what makes them good ligands as compared to others on the periodic table is this soft matching that you get with many, particularly late transition metals. And while these are sometimes just spectator ligands, they can have a tremendous impact on the properties of the metal, the metal center. So one descriptor that we've seen already, but now we'll rigorously define it, is this descriptor of bite angle, which I've drawn here as the angle that's formed between in a bidentate a bisphosphine ligand, for example, or a PN ligand or an NN ligand. The angle that's formed between these two ligands as they coordinate to the metal center, drawn in orange here. And as you might, so this can be measured in a couple different ways. You could, for example, get a crystal structure and measure empirically what the solid state bite angle is. And so if you read reviews on this topic, you'll sometimes see different bite angles quoted for the same ligands, and that's probably stems from how it's measured. But one term that's useful is this one called natural bite angle, where the only thing that's taken into account is the ligand based on molecular mechanic calculations. Okay, so we'll do a quick poll here to probe your or to test your intuition of the bite angle for these three ligands shown: BiNAP, DPPE, and Xanthos. And Xanthos, you can actually see, if you want to look ahead, can coordinate either in a cis fashion or cis spanning fashion or trans spanning fashion. So in this case, it's drawn as cis spanning fashion. So, okay, so rank these three in order, and then we'll see how your intuition holds up. Okay, let's give another 5 seconds and then you can close up. Oh, we've got 100% response. Okay. So it ranked in terms of increasing bite angle. So it looks like there's some disagreement here. I think there are a couple questions. The first one you maybe want to consider is, let's compare DPPE and Xanthos. Those, at least the phosphines, should generally be kind of like the backbone atom should generally be coplanar with the phosphine. So maybe is most intuitive to think about. DPPE has a natural bite angle of 85 degrees. Xanthos, much larger. It's generally thought of as a wide bite angle or transspanning ligand, is 111. I think the vast majority of people in the class had that order correct. And then the question is, where does BiNAP fit in this, along this? And this is not necessarily obvious just from looking at it as drawn, because BiNAP, as I've tried to represent here, has this really intense dihedral angle. I mean, you really need to look at this in 3 dimensions. It basically sits like this. So that the natural bite angle ends up coming in the middle here at 92 degrees.
Can I ask a quick question?
Yes.
So you mentioned that 110 is within the range of transspanning ligands. What's the threshold of that?
It probably is metal dependent, because it's going to depend on yeah, it's a good question. I think it will depend intimately on the size of the metal that we're talking about here. I guess Xanthos is probably close to the border because it can be cis-spanning or trans-spanning. There are some that are exclusively trans-spanning that have wider bite angle. The Xanthos is, you know, is kind of like this. There are some that are like this, and they can only be trans-spanning or monodentate. So I would guess Xanthos is close to a borderline case newer.
Thanks.
Yeah. And if we think back to our reductive elimination lecture, one of the things we said is that wide bite angles lead to more facile reductive elimination through the squeezing out principle. And the one exception would be then if it's so wide that it becomes trans-spanning, and then the two groups can't be in a cissoid relationship. Any questions on that? So one of the special properties that phosphines have, particularly in comparison to amines, is that they undergo they have a slow barrier to, a high barrier to inversion, and undergo inversion at phosphorus slowly. This originally was determined in the 70s by Mislow from Mislow-Evans reaction fame. And so there's some interesting chronology here. When this was first, when the inversion barriers to phosphorus were first rigorously established, this was contemporaneous, as we'll see, to when some of the early homogeneous hydrogenation work was going on. So that immediately led people to start thinking about ligands that were chiral at phosphorus and whether they could be purveyors of stereochemical information in an anti-selective reactions. And one of the very early manifestations of that idea from Knowles is shown here. And based on this result, it was ultimately developed into DIPAMP, which is a C2 symmetric. It's chiral at phosphorus, but also has this C2 C2 rotation axis. And we'll come back to this. So I'll just go through it quickly now, and then we'll come back to this in the context of other ligands for an anti-selective hydrogenation. So just to rehash something we already went through quickly in the structure and bonding lecture is just what the simplified MO picture of phosphorus binding to a metal, phosphines binding to a metal looks like. So they're obviously strong sigma donors, and we said that they're also pi acceptors. Early on I have this in a dotted box, and I say, please disregard if it's confusing, because actually when I was looking through my notes, I was like, why do I have this in my notes? I can manage to confuse myself. You know, I think one of the explanations that might come to your mind in rationalizing why phosphines are good can engage in pi back bonding, and this, if you're thinking this way, you're not alone. A lot of chemists thought this in the early days. You know, it can be measured directly from CO stretching frequency that phosphines are pi acceptors, and then the question is why and what orbitals are involved. Chemists in the early days thought that maybe the d orbitals, that these 3D orbitals that are accessible in phosphorus might be involved in back bonding, and that's shown here. But this turns out to at least not be the major one that's responsible. And what we covered before was that the sigma star antibonding orbitals are typically what are thought to be responsible for being pi acceptors, and the actual reality, if you want to take one, so I think for all intents and purposes, you know, this is what you should be thinking in the class. But if you do want one more step in terms of detail, you can take a look at this sigma star 3D mixing model, which you know, in a rough approximation, superimposes the sigma star antibonding model with this empty 3D model, and that's probably the most accurate depiction, but with the sigma star being the major player. So pay attention to what's on the left on my notes, and if what's on the right is confusing, then you don't have to think too much about it. Okay, let's very quickly now do problem of the day number 3 from last time, which is just a quick hitter. Let me share that. Somehow I can't open my Finder window. Okay, problem of the day number 3. So this is just asking us to rehearse what we just covered in terms of phosphine binding. So first, let's consider nickel tetracarbonyl, and then replacing one carbonyl with a generic phosphine ligand, any of those shown, trialkyl, triaryl, phosphite, and then what you would expect to happen to the CO stretching frequency. So that's the first question. So let's see. Omar, let's get you on the hook for both parts here. Nickel master, aspiring nickel master.
So I think that the phosphine ligand will make the nickel center more electron rich. So back bonding into the CO ligands will be much stronger. So it'll make it more like CO double bond in character. So I think it'll have a lower wave number than just regular nickel CO4.
Okay, and then pause here. I think do we have a poll for the second part, man? Okay, so then based on what Omar said, let's poll for part B. We'll see if we're all aligned here. And then Omar, you can explain your thinking on this one. So part B just asks now this isostructural series where we go trialkyl, triaryl, and then phosphite, which is trialkoxy or aryloxy, what the stretching frequency is. Okay, we're waiting on a couple people, so please, if you don't know, it's okay to guess. Okay, the plurality was 3, where we left to right, we're going T-butyl, phenyl, phenoxy. So maybe Omar, is that what you got? And then if so, why? If not, why not?
Yeah, that's what I got. I think that the terbutyl group is the more donating through inductive effects out of the other ones, and then I think that it would follow in that order. So you would expect T-butyl to have the lowest frequency, then phenyl, and then phenoxy.
So it looks like one of the points of confusion was how phenoxy fits. And why did you identify the phosphite as a stronger pi acceptor?
I guess maybe the sigma star of the phosphine oxygen bond is much larger, so than just like a phosphine carbon.
Okay, larger or lower energy sigma star. I think it'd be a way to frame that. Okay, so let's take a look at the data here. Hopefully you can read my handwriting. These are all in wave numbers.
I can't see your iPad.
Oh, thanks, Camille. That would help. Okay, there we go. So I even threw in the trifluoro here for comparison. I think this maybe seeing this extreme case might be helpful. And then nickel tetracarbonyl itself is 21, 25. So all in wave numbers. Here's the original, not the original reference, but a reference that summarizes all of this. So I think Omar explained it well. When you have these lower lying sigma star antibonding orbitals, they're better pi acceptors. So phosphites are identified as strong pi accepting ligands. And then an extreme case is trifluorophosphine, which people describe as almost as pi accepting as CO itself. And that's at least corroborated to some extent by the CO stretching frequencies.
I have a question.
Yes.
When you have something that is like phosphine that's sigma donating and pi accepting, that's ultimately still removing more electron density from the nickel. Like, because it's doing both, right? It's adding electron density by sigma donation and removing by pi back bonding.
Yeah, and even CO is both a sigma donor and a pi acceptor. I mean, it's a complicated point. Like in this series, we're looking at things with respect to CO, and CO itself is a sigma donor and a pi acceptor. So your point is well made, Alex, which is that you have to consider both, and thus you also have to consider the metal that's involved. Is it early or late? Is it inherently, is it low oxidation state and thus more donating? Inherently or higher oxidation state and thus more accepting, or more electron rich versus more electron poor, respectively. So it's not always just a super clear cut thing to understand. Okay, very good. Let's keep plugging forward then, so we have enough time to get through the hydrogenation part. So in terms of steric parameters, in addition to the bidentate case where we talked about bite angle with monodentate phosphines, there's a principle called cone angle. Originally, this was developed by Tolman, and he actually did it by building physical models like plastic or maybe wooden ball and stick models and measuring with the protractor what the angles of these ligands are. So this reflects the fact that if you think about phosphine in three-dimensional space, it really resembles a cone that's protruding from the metal, and thus you can measure this so-called cone angle and learn something about how crowding it is around the metal. The drawbacks of this are, one, that it only looks at a static picture of phosphines, but of course, particularly if there's alkyl branching, these are conformationally dynamic, and that's historically not taken into account. There's been recent work by Matt Sigmund and others to try to develop Boltzmann weighted average cone angles. And this doesn't work as well for ligands that are unsymmetrically substituted because the angle in the space filled in one axis is in one direction is much different than space filled in another direction. There's another parameter people use, and I will introduce it very briefly and then not talk about it probably ever again, because I think it's sort of come out of style, phased out of style, which is called solid angle. And this is like, I would think, you should think to like when you make hand puppets, you put like a light up to your hand, and then you make a hand puppet, and you have with the shadow that's projected on the wall. This is the same principle. You're using the ligand as a hand puppet and paying attention to the area that's blocked in the shadow of a sphere of defined radius, and then the ratio of the area that's blocked out in gray versus the square of the radius that you're using defines something about the percentage of that sphere that's blocked by the ligand. And the drawbacks here, probably one of them is obvious just from my meandering explanation, which is that it's a little bit non-intuitive, and two, it's not super easy to measure. And so this has been, I think, to a large extent supplanted by what we'll see very briefly, and we'll see shortly, which is percent buried volume. And yeah, this goes without saying that ligand dissociation is an important step, and this is reflects both steric and electronic contributions. And then I think one of the things that we have seen come up in several examples of, if you're just given a molecular formula and expect to think about geometry, then remember that phosphines tend to be bigger than other ligands and tend to want to sit trans to one another. So then closely related to phosphines are N-heterocyclic carbines. These are NN disubstituted carbines that are typically stable even when not bound to the metal. They're more sigma donating, they're weaker as pi acceptors, typically spectator ligands because they're really locked on the metal, much more so than phosphines actually. I think phosphines are more dynamic in general, and NHCs, with rare exception, when they're on a metal, they're on for good. And then because we're in San Diego, I should also highlight that there's another family of ligands called CACs, which are cyclic amino alkyl carbines, where one of the nitrogens of the NHCs have been replaced by tetrasubstituted carbon. So this juices up the HOMO, making it even stronger sigma donor. And they've also become better pi acceptors because, unlike, one way to think about it is, in this case, you've got a lone pair here and a lone pair here that are both able to provide some electron density to the carbene. Now you only have one, and so the carbene itself is a little bit more deficient in pi electrons. So the metal can provide that. And these I think are really coming on strong. It's an emerging class within the literature. We use them in our lab as well. And then Steve Nolan's group developed this concept specifically because cone angle does not apply well to NHCs. He developed this concept called percent buried volume for NHCs, but actually it extends well to phosphines. And there's an example from Abby Doyle's group here, Nature Chemistry paper, where she uses this with phosphines to great effect in a nickel-catalyzed series of nickel-catalyzed cross-coupling reactions. So here the idea, it's kind of related to solid angle, but is a little more intuitive. You basically pick you have your metal ligand, and then you pick a radius that you're interested in, and then you think about all of the volume in that sphere that is filled by the ligand. And you can calculate that using this tool called I don't know how to pronounce it, SAMVCA, or SAMVCA. It's an online tool. And this has advantages. It works with unsymmetrically substituted ligands. Like some of the other ones we've seen, it does not do well for conformationally dynamic ligands. You'd have to compute it in multiple conformational states and then do the Boltzmann weighted average. And then, there is the buried volume is dependent on the radius that you choose to measure. And so I would say that's like necessarily a drawback. It could be a feature depending on your perspective. And then the other thing is that it doesn't really capture the full electric field of the metal ligand complex. It doesn't read out the electrostatics. And then something we won't talk about just in the interest of time, but you may have also seen in the literature these steric maps, these contour maps that look basically like topological maps, where you can show the full in three-dimensional space, the full sort of steric profile around a metal center, and then you can overlay electrostatics if you wish to do so. Okay, now let's jump in to see how these concepts manifest in catalytic hydrogenations. We'll go through some of the basics here quickly because it's just restating things that we've seen. So it goes without saying that homogeneous hydrogenation is super important. But one of the things that's interesting, if you dig into this area of study, is that until about the 1960s, there were no known homogeneous processes that could compete to any extent with heterogeneous or biocatalytic processes. This whole field of homogeneous catalysis basically didn't exist, and it was really an open question. Is it possible to develop a homogeneous catalyst that could compete in terms of efficiency, not even selectivity, just efficiency with heterogeneous catalysts? And so you see the term first coined by Melvin Kelvin, a familiar name in the 1930s. We're familiar, probably many in the audience have used various heterogeneous catalysts. I've used many of these myself, and you know that typically the recipe is you have some nanoparticulate metal like palladium or platinum that is dispersed upon some type of solid support. Sometimes it's mesoporous carbon or there are other supports as well. And we talked about some of the advantages or disadvantages, heterogeneous versus homogeneous. And then asymmetric processes. I mean, one of the things that's always interesting, I always find fascinating is like to read OPRD and actually just ask yourself this question: where do all the chiral centers in the drug molecules come from? And they normally come from actually a small number. They either come from the chiral pool or a small number of reactions, and most of them are hydrogenations. So typically, if you see a secondary C oxygen or nitrogen bond that comes from some type of catalytic hydrogenation, or it can, and if you see a tertiary stereogenic center, it almost always coming from a hydrogenation. And then there are two flavors of hydrogenation that we'll talk about. We'll focus mostly on classical, and then there's another process called transfer, where typically a donor like hydrogen donor like isopropanol is serving as the H2 source for hydrogenation of a carbonyl compound. So two general mechanisms that you'll see at play. One we call a hydride mechanism, and the other we call olefin mechanism, and that's just defining which is binding to the low valent metal center first, either H2 or the olefin. And so depending on they will ultimately converge to the same key intermediate, which is this metal olefin dihydride. But in the first case, you get H2 coordination, oxidative addition, and then coordinate the alkene, and the order is opposite in the other. And I think that one of the key, the reason I present it like this is that some of the earliest examples of hydrogenation catalysts fall cleanly into one bin versus the other. So this was an important point in terms of the early mechanistic history of this area. Okay, so let's talk about some key, I'll leave this up in case anyone can jot down. Some key early historical developments. So I had mentioned previously Wilkinson's discovery and development of triphenylphosphine as a ligand for homogeneous catalysis was a game-changing discovery, and we've seen the Wilkinson catalyst now many times. So maybe one of the things that you haven't thought about, or if you have, then you'll be able to answer this question, is how would you make Wilkinson's catalyst? And there are multiple possibilities. So you're not you have a good chance of being right. So Tim, is Tim here?
Yep.
I can't see it on the second screen. Tim, so how would you make Wilkinson's catalyst? I've given you options here from rhodium-3 or rhodium-1, but historically the first one was this rhodium-3 route.
Okay. I think if you maybe if you start with I don't know if it's rhodium chloride and try and reduce it down with just phosphine, triphenylphosphine.
I love it, Tim. This is that's great. So I think your intuition is spot on here. You know, normally like metals, if you want to take things back to their simplest form, typically metals want to be in a higher oxidation state, just because of air, you know, like their air compatibility. So in the case of rhodium-3 is a good place to start. And then you said rhodium chloride. Chloride salts are often good starting points because ultimately these are made from like dissolving the metallic form in HCl or just extracting it using HCl. And then you said phosphine. And you want to use phosphine as ligand and as reductant, which is great. What would the byproduct be?
I don't want to say chlorine gas.
Well, you're using the phosphine as the reductant, so that by definition, then the phosphine's getting oxidized. So
phosphine oxide.
I think more precisely, the dichlorophosphine, phosphorus 5, which then upon treatment with water makes the phosphine oxide. Beautiful, Tim. And so this was the first synthesis of Wilkinson's catalyst. Congratulations, patent it now. And that works well for triaryl phosphines, but it has this disadvantage that you can't easily substitute other phosphines there. So later they developed a route that's a little more steppy, but more modular. And that's from the ethylene, rhodium-1 chloride dimer. So that I'm abbreviating the dimer as such. And then another advantage of this route is that you can titrate in your ligand to metal ratio by controlling the equivalence of the phosphine, something that you can't do when you need to use the phosphorus also as the phosphine also as a reductant. Okay, so in terms of reactivity,
Hi, Gary.
order-
Just a quick question, actually. Yeah. So, like, why only triaryl phosphine work for the generation of the Wilkinson catalyst with the rhodium-3?
Yeah, it's a good question. When I guess I think empirically that's the case, but what the underlying reason why is it's an interesting question.
I mean, is it because of the compatibility of the solvent? Because, like, I mean, trialkyl phosphine is more sensitive, so it may react with the solvent. But then,
it could be, or the water. I mean, the precatalyst comes as a hydrate, so it could also, that could be problematic. You might struggle. I mean, you could also potentially not get. If you're using trialkyl phosphines that are too big or too small, you might get mixtures of, n equals 2, n equals 3, n equals 4 that are hard to separate. I'm not sure about that, Wayne, but I can look into that.
And also, like, does like 3 aryl group need to be the same, or like can it be different?
I think they could be different.
Okay, thank you.
Yeah. So in terms of reactivity, I think this probably tracks to at least a first approximation with intuitively how we think of alkene reactivity. So cyclic internal alkenes, this is like a kind of a special breed of internal alkene because the steric bulk's always tied back. So when I see cyclic alkenes, I kind of think that they're not normal internal alkenes. So these are reasonably reactive, and then terminal are reactive, and then you start to see reactivity dropping down. 1,1 disubstituted, 1,2 disubstituted. Again, a common theme that Z is more reactive than E. Sterically, it's more accessible, easier to get onto the metal, and then has more potential energy. And then trisubstituted, and especially tetrasubstituted, do not work well with Wilkinson's catalyst, and that was a known limitation, irrespective of whether it's internal or terminal. So the reaction is cis selective or cis stereospecific, stemming from the stereospecific migratory insertion and stereospecific reductive elimination, and then these reactions operationally could go at ambient pressure and temperature. So some mechanistic observations. from the early days, if you ran a reaction in a mixture of H2 and D2, you would see only H2 hydrogenated product, only D2 deuterated product. You would not see a mixture, which is consistent with a dihydride mechanism. In a monohydride mechanism, you might expect to see mixtures of products. And then this is used as the archetypal, Wilkinson's catalyst is used as the archetypal example of a hydride mechanism. I'll stay on this mechanism here for a minute to sort of unpack this. So let's start here. This is our pre-catalyst. Let's see, Sunghan, what is the, do you want to do a quick electron count on this?
So I think it's rhodium 1 and D8.
Okay, and then 4 ligands, so that gets us to what?
16.
Okay, 16 electrons. So that means that in principle, it can directly coordinate H2 and then make the dihydride, which will be an 18 electron complex. But there's also an alternative pathway, which is the one drawn here. So if this is 16 electron, then this would be 14 electron. And then the 14 electron species could also bind to H2, form the sigma complex, undergo oxidative addition to make this now 16 electron species. Thank you, Sunghan. And one of the interesting things is that if you monitor this by NMR, this is what you see, the complex shown in orange, but actually the cycle that is productive for catalysis is through this initial loss of the phosphine ligand. So again, showing that the species that's most stable is not necessarily the one that's doing the lion's share of the work on the catalytic cycle. So loss of phosphine, coordination of H2, oxidative addition. Now, the nice thing about this pathway is you have a built-in open coordination site. You don't have to lose a phosphine from this 18 electron dihydride complex. So you can lose phosphine, or so you can then bind the metal, and then it's a classical hydride mechanism, as I said. Migratory insertion. Migratory insertion to make a rhodium 3 alkyl hydride, and then reductive elimination to close the cycle. There's another off-cycle process that can happen from direct coordination of the olefin. So it's kind of like with the catalyst that prefers a hydride mechanism, if the olefin coordinates too early, then that can also be deactivating, and that's what's shown here. So when we covered this idealized catalytic cycle from the Hartley textbook, we talked about these various deactivation pathways. So here's a reversible process that can take the active catalyst off cycle and be essentially a catalyst reservoir. And then if we compare, let me put this in a different color so it's clear. The two possible oxidative addition steps. There is a 10 to the 4th rate difference. Okay, let me leave that cycle. Yes.
Can you comment on why there's such a large rate difference? I would have expected that, I guess, the 16 electron complex to be more electron rich and therefore be able to engage more in oxidative addition versus the other complex, which is 14 electrons.
Yeah, it's a good question, Noor. I would guess, so I think that explanation is reasonable. And so then I would guess that it, or I guess my explanation would be then that the H2 binding step must be what is effectively rate controlling there. So in the 16 electron complex, though you have a free coordination site, it stands to reason that it's that the rate of coordinating H2 is slow compared to the other pathway.
That makes sense. Thanks.
Yeah.
One more thing, Kiri.
So there are some hidden, yeah, one of the things that I'll just comment briefly is there are some hidden intermediates here, like, you know, upon coordination of H2, there'll be a sigma complex that's formed. And so, you know, I think within each of these elementary steps, there are some hidden intermediates that we don't draw just because drawing all of them would be exhausting. Was there another question?
I was gonna ask the 1-2 migration and then reductive elimination is going back to the 14 electron complex.
So, okay, so you, from the 16 electron complex, then you coordinate the alkene to make an 18 electron complex. Migratory insertion will then get you to a 16 electron complex. And then reductive.
So the reductive elimination step.
Oh, sorry.
Going
Thank
to
you.
the...
Thank you.
Okay.
I see the problem. Yeah, thanks. Thanks, Carter.
Yeah, I think another comment on this 16 versus 14 electron oxidative addition is that there's like some notes on oxidative addition being easier from an odd coordination number, like 3 coordinate. And then similar with reductive elimination, that sometimes is better from 5 coordinate than 6.
Yeah, thanks, Matt.
Yeah, that just has to do with the geometries that you go through from 5 to 3, or conversely from 3 to 5. Just the movement of the ligands minimizes the energy for those geometries.
Okay, so let's, yeah, thanks for the questions and discussion. So let's go ahead and move on to the next category, which are the Schrock-Osborn catalysts. And one of the things is interesting, if anybody's watching closely and you pay attention to the year, you see that Wilkinson's catalyst, that was in the mid 1960s. And then the Schrock-Osborn series picks up in the late 1960s. And this is at least in part because Osborn is a former student, or was a student, and became a former student of Wilkinson, and Schrock was a PhD student with Osborn, and so I think Osborn, you know, using his experience from the Wilkinson group, likely was reflecting on what some of the limitations with that Wilkinson sort of first generation family of homogeneous hydrogenation catalysts are, and came up with this alternative design. The key feature is that it's a cationic, now rhodium 1, and it's a family of catalysts that are all structurally related. So there's typically a non-conjugated diene that's serving as one ligand, and that can either be COD or norbornadiene. Norbornadiene I have drawn out here, and this example will cover for the problem of the day. And then 2 monodentate phosphine ligands or 1 bisdentate phosphine ligand. So I have drawn over here like DPPE, for example. And then I think you probably start to see how this sets the stage for these chiral bidentate phosphine ligands, which built on this same design. And so here's a more Okay, and these need to undergo some activation process to get on cycle. So let's consider that now for the problem of the day. So I'll keep this screen share enabled so I can just jot down notes, but I'll read out the problem of the day. Oh, it's actually a COD. The problem of the day is with a COD, but I'll just do it with norbornadiene, and that we can all agree that the insights will be the same. Okay, so this needs to undergo some process upon treatment with olefin and H2 to get on cycle. So what do we expect might happen, Camille?
Will the alkene ligand dissociate the norbornadiene?
Okay, so let's think that through. So after it would dissociate, the norbornadiene would associate, then what would happen?
You could do oxidative addition, or you could coordinate your alkene of interest.
Okay. Maybe first, let's just quickly do an electron count of this rhodium, cationic rhodium complex. So what is this in terms of overall electron count? Camille, you got rhodium 1.
Is it 16 electrons?
Okay.
Okay, so then it probably won't lose. Maybe like part. Could like one of the alkenes of norbornadiene dissociate? Or it'll just oxidatively add H2.
Okay. And then what would happen?
Then you could lose norbornadiene.
So how would you lose it? You would dissociate norbornadiene?
Yeah.
So oxidative addition to make a norbornadiene dihydride, and then dissociation of norbornadiene. Is there anything else any other way that the norbornadiene could get off the metal?
Could it do ligand exchange with the alkene that you're hydrogenating?
Okay.
Or it could be hydrogenated off.
Ah, okay. There we go. So I'll draw this in cartoon form. So sorry if this is confusing. So I think Camille proposed this dihydride adduct. Is this right, Camille?
Yeah.
And then you said hydrogenate off, which means essentially a series of migratory insertions and CH reductive eliminations. So you only need, I guess you only need to do this once to get it off, but then because it's a strained alkene and reactive, it would probably happen a second time. And then your propagating catalyst would now be I'm writing in shorthand here just to save time. With 2 solvent molecules that I'll draw as S. Still in cationic form. And so some of the features here empirically, it was found that bidentate ligands are more reactive than the monodentates. There's this interesting observation made here that the cationic versions of these catalysts have different reactivity than neutral monohydrides. So you could imagine from this sort of dihydride, if metal hydrides come in many flavors. They can either be protic in character or hydridic in character. But if you or them in the middle. But if you take this dihydride and treat with base, you can lose one of the hydrides by activating that protic form and get to a monohydride, and then that is a deactivation mechanism. And so practically they get around this by normally running these reactions in the presence of a little bit of H+ to maintain always the dihydride state. And so the propagating species is this rhodium L2, S2, 2 solvents species. And this is believed to involve a classical olefin-based mechanism. The way I remember this is that, the catalysts themselves have olefin ligands in their pre-catalyst form. To activate, they coordinate H2, oxidatively add, and that's what they like to do. They like to have the olefin bound, then undergo oxidative addition, and then transfer hydrogen. So I sort of like, that's an easy mnemonic. They have olefins as ligands. They prefer the olefin mechanism. But after I tell you this mechanism, this mnemonic, then I'll tell you an exception, or at least partial exception to this, which is the next family, Crabtree's catalyst. So that Crabtree's catalyst is drawn here. Does anyone want to do a quick electron count on this one, Stone?
So we've got iridium 1. 1 second. It's a D8 complex, and it's 16 electrons.
And I think one of the distinguishing features for Crabtree's catalyst compared to the Schrock-Osborn series is now you have an even weaker coordination assembly. You basically traded one of those phosphine ligands in the Schrock-Osborn for a more weakly coordinating pyridine. So this thing is really hot to trot. It's a very reactive catalyst. And there's some interesting, I would just draw everyone's attention to this review by Crabtree, which, Crabtree has such a colorful and unique writing style. It's definitely a great read. And one of the things that he comments on in terms of the discovery of the development of the Crabtree catalyst is that the Schrock-Osborn and Wilkinson's catalyst, that research generally was done in ethereal polar solvents. And the Crabtree's catalyst does not work well at all in those solvents. So it was actually by some serendipity that they ended up running some experiments in DCM and chloroform, and found out that it's a remarkably reactive catalyst in those solvents, but not in highly coordinating solvents. And so it's one of these things where it would have been really easy to miss that. And that's part of Crabtree's reflection there. And so one of the interesting things, and this was known in the early days, is that if you take iridium-1, Crabtree's catalyst, or other related iridium complexes, which is a yellow in solution, and then you add H2, it will go colorless, and you'll get clean formation of this dihydride. And so it was known for some time that you could make iridium-3 dihydrides of this type. But I think the key insight was using weakly coordinating solvents and this weaker coordination environment, that combination is what really enabled this dihydride to actually engage in some productive chemistry. And indeed, as you see here, this is really one of the, still to this day, one of the most active homogeneous hydrogenation catalysts. I think even in this department, there are many examples in total synthesis where Crabtree's catalyst works and everything else that was tried failed. Mechanistically, this is a little bit more complex. I think there's evidence supporting that it could be a hydride pathway or could be an olefin pathway. Both, there's evidence for both. I think the consensus at the moment is the hydride pathway is more important, more responsible for catalysis. And then there's also some ambiguity surrounding the oxidation state, whether it's a 1,3 redox couple or a 3,5 redox couple. I won't go into those details just in the interest of time. Okay, let's now consider problem of the day number 2. I will end my screen share and do a re-share so we can see it. And this one also has a poll associated with it. Okay, so there are 2 parts. The poll is only for part A. So this is illustrating one of the interesting and semi-unique features, not totally unique, but prominent kind of reactivity and selectivity paradigms that you see with Crabtree's catalyst. So it's asking you to consider which is the major product in this hydrogenation of the alkenyl ketone substrate. Okay, we're about halfway there, so please register. I'm going to, and also take a look at B, which is just asking for 2 products of this hydrogenation of this alkenyl alcohol, and then to rationalize something about product selectivity as a function of the substituent. So take a look at that as well, because I'm going to reshare my iPad. Oh, I just closed the poll. Oh, thanks, Van to the rescue. Okay, the majority voted for A, and A was with both methyl groups down. So is anyone who, let me see, Noor, did you answer A?
Yes.
Why A?
So I would think it's directed. So the carbonyl is coordinating to the iridium and directing the facial selectivity.
Aha, okay. So let's draw out the intermediate that Noor proposed as well. So you said it is directed.
Kiri?
Yeah.
The structure you have drawn here is different than the one you have on the problem of the
yes,
handout.
right.
So I'm just wondering, like, okay.
Thanks. Yep. Yeah, I mean, there's this question about, you know, how directing it can be if it has to go transannular, but it is still a directed pathway. Okay, so this is a directed addition. So we get, I think there might have been some, I suspect there may have been some people actually thought it was directed, but then picked the wrong one because the methyls end up pointing down. Maybe people thought point up. Okay, and then number 2, Tiffany, or part B, Tiffany, what do you think?
So I guess you could still coordinate in this case.
Okay. So what are the 2 possible reaction, 2 possible products?
So I guess either on the same face or the opposite face.
Okay. And then how would you expect, oops, the product ratio to change as a function of, let's draw this up, the R group identity?
You would favor approach from the opposite face of the R group for a bulkier.
So let's draw out the directed and non-directed products. And you said a bulkier substituent, namely the methyl, is going to favor the non-directed pathway. Is that right? Does it makes it harder to coordinate?
Yes, I guess.
Okay. I buy that. Anybody disagree?
Well, I think you do need to see the conformation of the coordination when having the alcohol directing it. I think like the alcohol need to be axial to direct the hydrogenation to the alkene. So yeah, the methyl group actually favors the hydroxy group at the axial position. I think so. So.
Well, yeah, but the starting material is alkene containing in the 6-membered ring, so it's not you know, strictly like axial equatorial model. When I understand what you're getting at, but yeah, I think Tiffany got it right. Here's a reference from Gilbert Stork's group. It's Dan Kahn and Gilbert Stork. Interesting read if anyone wants to check out the data for that. Okay, there is some deactivation pathways with Crabtree's catalyst. In the interest of time, I won't get into this too much detail, but I think this ultimately stems from the fact that it's a pretty weakly coordinating ligand set, and so you can make hydrides, and then the hydrides, as we've seen, can bridge. You can form these complex bridged hydride species, which are not on cycle. And then maybe we just take a couple more minutes and do this problem of the day number 3 to talk about this last part, catalysts that react via monohydride intermediates, and then we'll call it a wrap. Okay, so let me read the question here, and it's summarized with this reaction scheme, which is that Wilkinson's catalyst, as we've seen, can hydrogenate terminal and internal olefins. In contrast, this species drawn is only selective for hydrogenating terminal olefins. So first, let's take a look at the electron count of this pre-catalyst and also just what the structure would look like in 3D. And then let's rationalize this explanation, this empirical trend based on the mechanism. And these are this is illustrative of this broader category of reactions that function via monohydride intermediates. Okay, Fang, what is the electron count for this complex?
So it's rhodium 1.
Okay.
And it's a D8.
Okay.
So you have 18 electrons in total.
Okay. And I've drawn it this way just to help move things along. Why do I draw the phosphines here all coplanar, Fang?
I guess it's due to a steric effect.
Okay.
If you put all those phosphine together, it will be much more unlikely to. Yeah.
Okay, so if it's 18 electron complex, then what's the first thing that needs to happen?
You must lose a ligand of the.
Okay.
Yeah.
So first things first, we free up a coordination site, and then what would you expect to happen next?
You can either coordinate with olefin or coordinate with hydrogen. So in this case, it's the olefin.
Okay.
Yeah.
If you did coordinate the hydrogen, what would you expect to happen?
I guess it would go back or to form like formate or something.
Yeah, I guess you could react the carbonyl, but let's say you coordinate H2, and then even if it were to oxidatively add, it would probably just reductively eliminate H2, and so it would end up being non-productive. Okay, so then what's going to happen next, Fang?
You do a oxidative addition. Sorry, not just addition to the olefin. Sorry, what's that?
Okay, migratory insertion. And then now you said
Oxidative addition of the hydrogen molecule.
Beautiful. Okay.
And reductive elimination to get the final product.
Okay, so the last part of the question asks to think about potential byproducts, and then we'll wrap things up. What could a potential, how could this go wrong, Fang?
The carbonyl group might migrate to one of your resting state or your intermediate.
Okay.
So yeah.
This is indeed an active hydroformylation catalyst. You probably need some positive CO pressure to keep that going. But it could be a deactivation mechanism. What else could go wrong?
it could be the alkene migration. You form like you make your terminal alkene to disubstitute alkene.
So maybe just for clarity, I'll redraw this just so that I don't confuse everybody. So I think Feng rightly pointed out that now you can get isomerization. And so you can migrate, isomerize the alkene from terminal to internal. And we already know that internal alkenes are not compatible with this family of catalysts. So that would be then a deactivation mechanism because you're building up internal alkene concentration. That's going to not be perfect. And the key here is that you have this intermediate where you have an open coordinate, an alkyl with an open coordination site and beta hydrogen atoms here. And so remember, this pathway with monohydride is unlike the other two because we make this monohydride, we undergo beta hydrogen elimination, and then we have this alkyl, metal alkyl intermediate that has an open coordination site that we need to coordinate H2 to before something else happens. And the something else happens is an intramolecular process that can be fast, beta hydride elimination. So that's the challenge here with using these pre-catalysts. Okay, I'm sorry, I went over today, but I did want to get through that point. Okay, any questions on that? Otherwise, we can.
I have a quick question about the last point.
Yeah.
Can you add like chloride salt to suppress that beta hydride elimination, or would that? I'm pretty sure that would interfere with the hydrogen oxidative addition too. But
it's a good question. I think actually probably Valerie will show an example tomorrow if she talks about what she has talked about in the past, where you can directly suppress beta hydride elimination by just adding more L-type ligand. In that case, I think it's triphenylphosphine, and we've done that once in the group. You know, the issue is most of the time that doesn't work because you totally change the speciation of the catalyst when you start just adding more of any of the any of the ligands. But it's a good, I think intuitively it's a great suggestion, Noor.
I have another question, if that's okay.
Sure. Yeah.
I guess for the hydroformylation byproducts, I know that would change the electronics of the complex, but why don't you just try to substitute the carbonyl for something else that's not necessarily active in migratory insertion?
Oh yeah, that's a good question. I mean, the thing is there aren't that many carbonyl-like ligands that recapitulate all of the properties of carbonyls that don't also participate in migratory 1,1 migratory insertion. So for example, you might think isonitrile, alkene isonitrile or something like that. But those can also undergo 1,1 migratory insertion. And so it's not easy to recapitulate the exact CO properties of CO ligand. But again, it's a good suggestion. Or you could try, like we just mentioned, try fluorophosphine. That could be interesting potentially.
Thanks. Yeah, that makes sense.
But it's bigger. Those are bigger than CO. That's a problem. Oops. Let me just complete this part of the notes by saying internal alkene. Okay, we'll wrap things up here then. Thanks everybody for holding on here so we can get through this section. See you all on Thursday for Valerie's guest lecture.